Higher 11s and 12s. Today we're going to be looking at the last PowerPoint in our ecology unit for SL Biology, part of the IB diploma. In this PowerPoint we're going to be looking at climate change. There should only be one video. There will be some other videos and links embedded in this PowerPoint. They won't be in this video, but they will be accessible on the PowerPoint on the OneDrive, and we'll watch them in class as well. Let's begin. So as per usual, here are your need-to-know statements for this PowerPoint. I'm not going to read through these. If you'd like to write these down in your notes, this is a good spot to pause the video and write these down. But let's start by talking about greenhouse gases. So in general, the Earth we live on is currently kept warmer than it should be because of the gases in our atmosphere that retain heat. Now there's a lot of different greenhouse gases that contribute to that, such as carbon dioxide and water vapor. Now, carbon dioxide is released in the atmosphere by cell respiration in living organisms and by the combustion of biomass and fossil fuels. And this is by far, as we can see in this picture here, the most impactful of the greenhouse gases, carbon dioxide. So 82% over here, carbon dioxide. And we've also got water vapor. Water vapor is formed by evaporation from oceans and from transpiration in plants. The biggest difference with water vapor between the rest of the greenhouse gases is that water vapor itself isn't physically coming from human intervention. Okay, the other greenhouse gases we can always trace back to humans. Water vapor, we can't, really. Not by increased means, anyway. Other greenhouse gases, like I mentioned, so we're talking about methane. Methane is the third most significant greenhouse gas. It's released from marshes and other waterlogged habitats. It's released during the extraction of fossil fuels, from melting ice in polar regions. Another impactful greenhouse gas, nitrous oxide, released naturally by bacteria in some habitats, but also through the agriculture and vehicle exhausts. These aren't as impactful as carbon dioxide, but obviously still have an impact on the climate change in general. So, how can we assess the impact of greenhouse gases? So there's two different factors that we use to determine how impactful a greenhouse gas is in its role in climate change and how it is going to impact the Earth. One of those factors is how readily the gas absorbs long-wave radiation. So gases that have a greater capacity to absorb long-wave radiation will have a greater warming impact per molecule. We also look at the concentration of the gas in the atmosphere. So the greater the concentration of the gas, the greater its warming impact will be on the atmosphere. The concentration of a gas will obviously depend on the rate at which it's released into the atmosphere and how long it remains there. And we talked about that a little bit last week in the PowerPoint then. So, we're talking about long wavelengths and short wavelengths. What exactly does that mean? So, the warm surface of the Earth absorbs short wave energy from the sun, but then it re-emits that energy as heat at longer wavelengths. Most of those re-emitted wavelengths are infrared, with a peak wavelength of around 10,000 nanometers. The warm surface of the Earth, as I said before, emits longer wave radiation than it's physically taking in from the sun. And we can see that a little bit in this picture here. 25 to 30% of the short wavelength radiation that comes from the sun and passes through our atmosphere is actually absorbed before it reaches Earth's surface. So we already start to lose some of the energy as it moves through the atmosphere. 70 to 75% of the solar radiation therefore reaches Earth's surface and is converted into heat in the Earth's surface. That heat is now long-wave radiation. When that heat is re-emitted from the Earth, it goes back up towards the atmosphere. Now, 70 to 85% of this heat will be absorbed by the atmosphere before it actually reaches space and will be re-emitted again back towards the Earth, as we can see through these long wavelengths here. So, light comes in, trapped by the greenhouse gases, reflected off the Earth, comes back as heat down towards the Earth. How can this affect our climate change and our global climate patterns? So, our Earth's surface is estimated to be about 32 degrees higher than if there were no greenhouse gases. Now, obviously, that means we need the greenhouse gases to survive because the Earth is at a temperature that we can live on. Okay, but if the concentration of the greenhouse gases was to rise, our mean temperature would also increase due to more heat being retained in the atmosphere. Now, that doesn't mean that global temperatures are directly proportional to the greenhouse gas concentrations, because there are other things we have to take into account. Sunspot activity. Now, the global temperatures of our Earth will also influence other aspects of climate, such as the evaporation from water, which affects the rainfall, etc. And this is why scientists have predicted that an increase in greenhouse concentrations will lead to an enhanced greenhouse effect, which means we'll have more frequent extreme weather conditions. So we'll have more heat waves, more cyclones, more powerful tropic storms. Some areas will become more drought affected, while others will become more prone to periods of heavy rainfall. Changes to circulating ocean currents will also cause things like El Nino warming or La Nina cooling events to occur more frequently. So in general, global warming doesn't just necessarily cause warming, it's more extreme weather conditions in general. And that's where a lot of people get confused with what greenhouse gases and climate change actually are. So, what's the evidence to say this is a result of humans, that the world is getting warmer or the weathers are becoming more erratic because of humans? Well, there is this correlation. Okay. As atmospheric conditions of carbon dioxide have increased since the Industrial Revolution, we've also seen an increase in global temperature. So, at the end of the late 18th century, the carbon dioxide concentrations on the Earth were around 260 to 280 parts per million, ppm. Okay. That's the start of levels rising above natural levels. Since 1950, those levels have raised even higher, as we can see over here. So currently at a little bit into the 2000s, we're currently at around 380 parts per million carbon dioxide. Okay. Why are carbon dioxide concentrations increasing so much at this time? Well, in the late 18th century, we had the Industrial Revolution starting. The main impact of industrialization happened in the second half of the 20th century, so that's why we started this large increase here. Now, as you can see, as carbon dioxide levels are starting to rise, and we can see that in the blue line here, okay, the carbon dioxide levels in the atmosphere are rising because of the Industrial Revolution. We can also see that the mean temperatures of the Earth in this red line here have also started to increase, and how much they've increased. Okay, so we can see that there is that correlation between the Industrial Revolution, increased carbon dioxide concentrations in the atmosphere, and therefore increased temperature of the Earth. So, what's the reason for those recent increases in atmospheric carbon dioxide levels? Well, a lot of them are due to the increases in the combustion of fossilized organic matter, like we talked about last week. Okay, so after the 18th century, we had increased quantities of coal being mined and burned. In the 19th century, then we started doing oil and natural gas, as well as coal. All of these fossil fuels being burnt had this rapid onset from the 1950s onwards, and that coincides with the periods of the steepest rates in atmospheric carbon dioxide. So it's because of our reliance on fossil fuels. Now, there is this good video here that we will watch in class. You can play it on the PowerPoint on the OneDrive, and it's just from NASA talking about how carbon dioxide levels change over the period of a year. Okay, so I'll pause that there. We'll watch that in class. You can go there and watch that at home if you like to. Obviously, though, climate change is one of these, it's a very political topic. Some people believe it exists, some people think it's a complete myth. So part of the IB is you have to be able to assess those claims and those counterclaims and evaluate the fact that human activities are not causing climate change. Think about what reasons there are for opposition to climate change. Why do scientists defend their findings so vigorously? When you're doing this, you need to think about scientists are trained to be cautious about their claims, always basing their ideas on evidence. They're trained to give details about uncertainties, so that can give the impression that evidence is weaker than it actually is, because we're trained to look for the flaws in our data. Global climate patterns are very complex. It's difficult to make predictions about the consequences of further increases in greenhouse gas concentrations. And the consequences of changes in global climate patterns could be very severe for humans, and as well as the other species on Earth. So many feel there needs to be immediate action. So it's we need to do this now. There is a link here. If you click here, we'll go to BioNinja, where there's a whole lot of counterclaims and claims that you can evaluate. Lastly, talking about coral reefs and carbon dioxide. As well as contributing to global warming, carbon dioxide is having severe impacts on the oceans, and we talked about this a few weeks ago, that carbon dioxide is soluble in water. So over 500 billion tonnes of carbon dioxide has been released by humans since the start of the Industrial Revolution. and a large portion of that has dissolved into our oceans. That's led to a 30% increase in acidification in the oceans. The dissolved carbon dioxide in the ocean reduces the already low concentration of carbon ions in the ocean, which makes it difficult for reef-beating corals to absorb the carbon ions using their skeletons, and hence we're getting to this bleaching effect that we can see on the left here, and how our coral reefs are suffering. Again, there's another video here from Ace. I'll play it a little bit here, but we'll watch this in class. Another one that you can watch at home beforehand if you'd like, but we'll watch and discuss this in class as well.